Good morning, everyone. My name is Shazab Ali. Today, we're going to walk you through a deep learning project we built for automated hair loss assessment, specifically predicting scalp hair coverage as a continuous percentage from a top-down photograph with a self-adapted training loop. Let's get into it. The core problem we're solving is this. Right now, when a dermatologist or a patient wants to monitor hair loss progression, they're doing it visually, comparing before and after photos and using coarse clinical scales, like the Norwood-Hamilton classification. That process is subjective, slow, and highly dependent on whoever's doing the evaluation. What if we could just hand a phone to a patient, take a top-down photo of their scalp, and get back a precise number, like 72% hair coverage, down from 78% 6 months ago? That's the goal. We're framing this as a regression problem. Predict a single scalar label, hair coverage percentage from 0 to 100, directly from an RGB image. Hair loss is then just 100 minus that number. Before we get into our approach, let me briefly contextualize where this sits relative to prior work. First, Majid ETAL built a smartphone trichometry system using a dermatoscope attached to a phone to measure hair counts, shaft diameter, and density from a small magnified patches. Really impressive precision, but it doesn't give you a single global coverage number from a full head photo. Second, Chang ETAL used a digital microscope to map hair density and the terminal to vellus hair ratio at 11 fixed scalp locations. Their quantitative metrics correlate strongly with alopecia severity, but again, specialized hardware, multiple measurements, no single scalar output. Third, Chowdhury ETAL trained a multi-class diagnostic CNN for hair and scalp disorders with Grad-CAM explainability. Strong diagnostic accuracy, but it's a classification problem, not a continuous regression. Our work positions differently from all three. We're targeting a consumer and telehealth use case, any top-down photo, one number out, semi-supervised to make a use of unlabeled data, and Grad-CAM adapted for scalar regression to verify the model is reasoning clinically. Our dataset comes from a public RoboFlow hair segmentation collection. It contains a top-down scalp photographs that span the full severity spectrum, from completely bald to full coverage, everything in between. The raw dataset had 461 images, but it contained some non-top-down photos, side angles, angle shots that would have confused the model. We manually filtered those out, removing 26 images, leaving us with 435 usable labeled images. We split those into 305 training, 50 for validation, and 80 for testing. We also held aside a separate pool of approximately 200 unlabeled top-down scalp photos. These have no segmentation masks. They're purely for semi-supervised SEAL stage, which I'll describe shortly. Here you can see what the annotated data looks like. Each image has 2 segmentation masks, drawn in COCO polygon format. The green outline defines the total scalp region, both hair and bald scalp together. The orange or red region inside the marks, the bald patches specifically. Our job in label generation is to convert these 2 polygons per image into a single number. What fraction of the scalp is covered by hair? That's the target we train on. The math is straightforward. We rasterize the hair polygon and the bald scalp polygon into binary masks. The scalp mask is the union of both. Every pixel that's either hair or bald scalp, excluded the background like clothing and furniture. Then coverage equals hair pixels divided by scalp pixels, times 100. If an image has 0 scalp pixels, meaning the annotation is degenerate or mislabeled, we discard it. Everything else gets a scalar label in the range 0 to 100. Hair loss percentage is just 100 minus coverage. That's it. Dense segmentation collapsed into one regression target per image. On the engineering side, we built a PyTorch hair coverage dataset that reads a CSV of image paths and coverage labels. It normalizes coverage to the 0 to 1 range for numerical stability. Loads images as 256 by 256 RGB tensors, and pushes batches of 16 to the GPU. For augmentation, training images only get light transformations, a random horizontal flip, small rotations up to plus or minus 10 degrees, and mild color jitter for brightness and contrast. Validation and test images get only deterministic resizing. The augmentations simulate the real-world variation in phone cameras and lighting that we'd expect in telehealth deployment, and they help the model generalize better, given how small this dataset is. Our first and primary model is a ResNet50 pre-trained on ImageNet. We take the full ResNet backbone, all the residual blocks, and learn features from millions of ImageNet images, and we replace the final classification layer with a single linear unit. That one output neuron predicts normalized hair coverage, which we scale back up to percentage points during evaluation. We train with mean squared error loss, Atom optimizer at a learning rate of 10 to the negative 4, batch size 16 for 50 epochs. The choice of MSE is intentional. It penalizes large error more heavily, which matters because a 20-point error in predicted coverage is clinically much worse than a 5-point error. This ResNet50 baseline serves as our reference point. Everything we do after this is measured against it. To understand how much the model capacity actually matters for this task, we ran a second experiment with ResNet18. Same training setup, same hyperparameters, same augmentations, only the backbone changes. ResNet18 is significantly lighter, fewer parameters, shallower residual blocks, faster to train. The scientific question is the extra capacity of ResNet50 actually necessary for capturing the fine-grained texture patterns that distinguish 60% coverage from 70%? Or can a cheaper model match it? Spoiler, it can't, but we'll get the numbers. Now for the most novel part of our pipeline, SEAL, which stands for Self-Training with Estimated Accuracy of Labels. The core idea is teacher-student self-training. Step 1. You train your baseline model, ResNet50, on the fully labeled 305 image training set. That gives you a decent teacher model. Step 2. You take the 200 unlabeled images and run each one through the teacher 3 times with light augmentations. A flip here, a brightness change there. You get 3 coverage predictions per image. You compute the mean of those 3 predictions, and also the standard deviation, which tells you how consistent the model is on that image. Step 3, the uncertainty filter. If the standard deviation is below 5 percentage points, the model is confident across augmentations, so we trust that mean prediction as a reliable pseudo-label. High variance images get discarded. We're only keeping examples the teacher is sure about. Step 4, we concatenate the original labeled set with high confidence pseudo-labeled images, and fine-tune the model on this expanded dataset for 15 additional epochs. The intuition is clean. The model bootstraps itself by labeling the data it's confident about, which gives it more examples to learn from, which makes it better, which would make future pseudo-labels even better, though we stop at round 1 here. The key constraint: this only works if the teacher is already good enough to generate reliable pseudo-labels. We saw exactly this inside of our results. Let's look at how training went. On the left is ResNet50's baseline training curve. The blue training loss follows a smooth, monotonic, downward trend. The model is learning consistently throughout the 50 epochs. The orange validation curve is noisier, bouncing between roughly 0.02 and 0.09 MSE, or mean squared error. This is expected with a validation set of only 50 images. Small sets are sensitive to which specific images happen to land there. On the right is ResNet18. The behavior is actually more stable. Both training and validation curves converge quickly and track closely together. But notice the y-axis. ResNet18 hits a higher floor, stable convergence at a mediocre level, versus noisier convergence to a better level. We want that later. Here's the full quantitative comparison across all 4 models. The winner on every single metric is ResNet50 plus SEAL. Looking at MAE, the ResNet50 baseline lands at 11.10 percentage points after SEAL. That drops to 10.60, a 7% improvement. R squared rises from 0.548 to 0.573 and 3 bucket accuracy, which measures whether the model correctly classifies a scalp as low, medium, or high coverage, jumps from 86.25% to 90%. ResNet18 baseline is at 12.24 MAE, which is worse but still usable. But look at ResNet18 plus SEAL. MAE jumps to 15.54 and R squared collapses to 0.39. The model got significantly worse. That's the teacher quality effect I mentioned. When ResNet18 generates pseudo-labels, those labels carry its error into the expanding training set, and the model amplifies its own noise. The lesson: SEAL is a powerful tool, but it requires a strong enough teacher model, and model quality gates semi-supervised improvement. The aggregate MAE number hides something interesting. Both models struggle in completely different ways depending on coverage severity. We split the test set into 3 buckets. Low coverage meaning 0 to 33%, which corresponds to severe hair loss. Medium coverage 33 to 66%, and high coverage 66 to 100%, meaning mild or no loss. For both ResNet50 and ResNet18 with SEAL, the error pattern is consistent. The high coverage bucket is easiest, MAE around 6 to 7 percentage points. The low and medium buckets are much harder, MAE around 20 points. This makes clinical sense. A mostly bald head and fully covered head are visually distinctive, but a scalp at 45% coverage versus 55% is subtly different. The model has trouble in the ambiguous middle range. This is also where the dataset is most balanced. We have too few moderate cases. Let's make this concrete with actual predictions. On the left, you see the same unlabeled scalp image run through both models. ResNet18 plus SEAL predicts 88.4% coverage with 11.6% loss. ResNet50 plus SEAL predicts 90.7% coverage with 9.3% loss. Both look visually reasonable for a head that shows some central thinning, but mostly hair. On the right, the 2 test images where we know the ground truth. For the top image, ground truth is 98.8%. ResNet18 predicts 93.5%. Error of 5.3 points. ResNet50 predicts 94.6% at 5.4 points. For the bottom image, ground truth is 100%, and ResNet50 predicts 94.6%. Error of 5.4 points. Both models are within roughly 5 to 6 percentage points of the ground truth on these high coverage images, which is approximately 1 step on the Norwood-Hamilton clinical scale. That's clinically reasonable. The model isn't perfect at percentage estimation, but it's directionally accurate and places patients in the right severity band. Now I want to explain how we know the model is looking at the right things, rather than learning spurious correlations from backgrounds or lighting. We use Grad-CAM, gradient-weighted class activation mapping. Here's how it works for regression. After the model makes its coverage prediction, a single scalar, we backpropagate the gradient of that scalar back to the last convolutional feature maps. Grad-CAM then computes a weighted sum of those feature maps using the gradient magnitudes as weights. The result is a spatial heat map showing which regions of the image most strongly influence the predicted coverage value. High values in the heat map, yellow and red, correspond to regions that, if attended to, increase the predicted coverage. Low values, blue, have little influence. One important clarification. People sometimes ask why we don't just overlay the original segmentation mask. The answer is that our model is not a segmentation model. It never outputs a predicted mask. The COCO segmentation annotations were only used to generate the scalar label during label generation. The model has no spatial output at all. Grad-CAM is the right tool to answer the question, where did the model look to arrive at this prediction? Here's Grad-CAM applied to ResNet50 plus SEAL on the same scalp image. 90.7% predicted coverage. The heat map is concentrated tightly on the central scalp region, with the hottest activation directly over the thinning area, where the hair is sparser. The model has learned without any explicit spatial supervision that the central crown is the most diagnostically relevant region for coverage estimation. This is exactly what a clinician would focus on. Now ResNet18 plus SEAL on the same image. It also activates over the central scalp, but look at how much more diffuse the heat map is. It spills into the surrounding hair regions and even into background areas like the person's shoulders and chair. ResNet18 is finding the right general area, but it's not localizing as confidently. This broader, noisier activation is consistent with ResNet18's weaker quantitative performance. Capacity matters for spatial precision, not just global accuracy. So let's wrap up the results. ResNet18 plus SEAL is the best model across every metric. MAE of 10.6, R squared of 0.57, and 90% 3-bucket accuracy. ResNet18 trained stably but landed consistently below ResNet50 on all metrics, and adding SEAL made it significantly worse. The central design insight is this: SEAL is a multiplier on your baseline. A strong baseline, ResNet50, R squared around 0.55, generates reliable enough pseudo-labels that semi-supervised training meaningful helps. A weaker baseline, ResNet18, generates noisy pseudo-labels that contaminate the expanded training set and hurt performance. Teacher quality is the gating factor for self-training. For any future deployments of this system, the recommendation is clear. Use ResNet50 plus SEAL and evaluate SEAL's confidence threshold carefully based on whatever dataset you are working with. A few honest limitations before we wrap up. First, class imbalance. The dataset is skewed towards severe hair loss cases. Both models perform well on high coverage scalps, MAE around 6 to 8 points, but struggle on low and medium coverage, where MAE reaches 20. That's a direct reflection of training distribution, not a fundamental failure of the architecture. Second, generalization risk. Because the dataset is narrow in distribution, we don't know how these models behave on different ethnicities, camera types, or lighting conditions. A telehealth deployment would require diverse data collection before we could claim reliability. Third, SEAL is sensitive. SEAL creates pseudo-labels where the model is most confident, which given the imbalance means more high-loss heads. This reinforces the underrepresentation of mild cases rather than fixing it. There are 4 directions we'd pursue to push this further. First, larger and more balanced data collection, specifically targeting mild and moderate hair loss cases, would directly close the bucket level MAE gap we saw. That's the highest leverage improvement. Second, vision transformer backbones. VIT and SWIN transformers architectures capture long-range spatial dependencies that CNN receptive fields miss. For a task that requires reasoning about texture gradients across the whole scalp, that could matter. Third, domain shift testing. All of our data, labeled and unlabeled, comes from the same RoboFlow distribution. Real-world deployment requires cross-camera, cross-ethnicity, cross-lighting, and validation. Fourth, stronger regularization. Techniques like mix-up, cut-mix, or stochastic depth could significantly reduce overfitting on a 435 image dataset without requiring any new data collection. These are relatively low-cost improvements that could push R squared meaningfully higher. A few of our references are here. We mainly focused on the MIT SEAL paper when coming up with this idea. With that being said, that's all I have for you today. Thank you for taking the time to listen, and enjoy.